Take it easy. Take it easy. Okay, so we are calculating the total binding energy and the binding energy per nucleon for lithium. And while it's not written here, lithium, if you recall, is the third element on the periodic table. So it has 3 protons, and as a result as well, it has 3 more neutrons to keep it stable. So we have a atomic mass number of 6. Now, to calculate our total binding energy, and then to eventually get the binding energy per nucleon, we're looking for a mass difference in lithium. If we actually look it up in a textbook, we would know that the mass of standard lithium is 6.015122 atomic mass units. But if we add up the protons, the 3 protons in lithium, and then we add up, so if we add up the 3 protons in lithium, and then we add to it the 3 neutrons in lithium, and we're going to ignore the electrons here. They're so small, they don't matter at all. Who cares? They're not even in the nucleus. Then this will give us our theoretical mass of lithium. And we know that this theoretical mass is going to be larger than our accepted measured mass of lithium. So if we subtract this measured mass of lithium here, the 6.015122, then that difference is the missing mass, okay? And we know that this missing mass is equal to the binding energy. So let's add up 3 protons, let's add up 3 neutrons, subtract what the actual lithium is, get that missing mass, which is the binding energy, and do a little bit of conversion there, okay? For our 3 protons, this is going to be 3 multiplied by 1.007825 atomic mass units. These decimals are so important. So make sure you don't miss them. We add to that the 3 neutrons, which is 1.00, and these are slightly more massive. So this is 8665 atomic mass units. And then we'll subtract 6.015122 AMUs. When we put all those together, we get a quantity here. We get some number. And if we recall, if we take this number, whatever we're going to get, and we multiply it by 931.5 MeVs, this is 931.5 MeVs per AMU. So our AMUs will cancel out here. We'll get a value, and it turns out that the value we're looking for here is approximately 32 mega electron volts. Okay, so doing this mathematics up here, taking this number down, and then multiplying it by the 931.5 MeVs should give you about 32 mega electron volts. And we got that unit of the MeV simply on the 931.5. Now, if we want to figure out how much binding energy exists per nucleon, this is very straightforward. This 32 MeV is the entire nucleus's binding energy. So if we want that per nucleon, which are protons and neutrons in that nucleus, a total of 6 of them exist. That's our atomic mass number. So we can simply take 32 divided by 6, and that's 32 MeVs per the 6 nucleons. And that's going to give us 5.33 MeVs per nucleon. Whooshing! And there, we're done. We have it. There's a ton of energy stored within the nucleus of these atoms. We see in this case, though, comparing lithium to helium, it looks like there's a little less binding energy stored in a lithium nucleus per nucleon than there is in a helium nucleus per nucleon. But there is a larger total binding energy here simply because we have more nucleons in that nucleus. So with that, this little example here is finished. Until next time, adios, and take it easy. Take it easy.